What's going on, everybody? Welcome to part 42 of our machine learning tutorial series. We've been talking about clustering with the mean shift algorithm, and in the last tutorial we built our very own custom mean shift algorithm that appears to be working pretty well. Like, we can run it real quick and like we've got our clusters chosen automatically. We feel like we're pretty darn smart. Unfortunately, this really only works when the radius is 4 or about 4. Otherwise, if you do something bigger or something, it doesn't work the way we intended. So basically, we've reduced this to a hard coding issue where we've had to ourselves implement some sort of radius that makes sense. The only reason we can choose 4 is we could kind of look at the data set and see, you know, a 4 radius would probably be a good radius for this data set. Okay, but that's no good, because what if the data set was 30 dimensions? You wouldn't be able to so easily look at it and be like, yeah, the radius ought to be about 4, or, you know, or whatever it might be. So instead, what we're going to do is we're going to put on some weight, and we are going to use that to help us basically automatically handle for finding the centroids correctly. So we're not actually going to use a simple radius. We're going to use a very large radius, but we're going to penalize points for the further they are from the current centroid in question. So that's going to hopefully give us much better results and make this code much more dynamic. Let's get to it. So first we're going to go radius, and we're going to set the default radius to none. So if the person really wanted to set a radius, maybe we might let them do some radius stuff, but I'm going to set that to none for now. And then we're going to say radius norm step equals 100. That'll make a little more sense when we actually get to it, so I'm not going to explain too much there, but we want to have a lot of steps in the radius and like a lot of basically bandwidths, and then depending on which one they're in, the closer they are to the centroid, the higher the weight or the value is for that data point. So that's kind of where we're going. So then we're going to say self dot, and then I'm just going to copy this, copy, paste equals paste. Okay, so cool. Now we're going to pop on over to the fitment, and basically before we define really anything, we'll just add it up here. We're going to say if self.radius equals none. What are we going to say? Well, we're going to say all data centroid. And what we're going to do is we're going to find the centroid of basically all of the data. So we're going to find the center of all of our data. And then so the way we're going to do that is just np.average data and then axes 0. So the same thing we've done somewhere down here, somewhere. Where are you? There it is, new centroid. Okay, so same thing we've done there. So we set that, and then we're going to say the all data norm equals np.linalg.norm. So this just gives us the magnitude from the origin, so data centroid. So basically from the norm to this data point, we're just finding like what about the average is, and then we're going to use that average to help us determine a decent overall radius to have, and then the steps and all that. So anyway, we do that. All data norm equals that, and then we're going to say self.radius. So now we're actually defining a radius. Will be all underscore data underscore norm divided by self.radius underscore norm underscore step, and that'll be all for now. So now we've got a new radius. It's that entire norm divided by the actual radius step that we're going to take. Now we're going to go into our while true loop, and we are going to, first we need some weights. So we've got, let's see, 4i in centroid. So this is our while true loop. We're going to leave that alone there. So while true loop, and then we've got 4i in centroids here, and then basically before we iterate through our actual feature set, we are going to define our weights. So we're going to say the weights are equal to I 4i in range of self.radius underscore norm underscore step. So this is just going to be a 0 all the way to 99 basically. So we're going to have weights from 0 to 99. And then we're going to reverse the order of this list. So ::(-1) will reverse the list. There's other ways you can do it, but this will do it. So now it's going to be 99, 98, 97, 96, and so on. Okay, so that's step number 1. What's going on? Harrison from the future here. as I was going through the text-based version of this tutorial, I caught this kind of stupid error here where we're defining the weights within the for loop. I mean, this was just me kind of like going through the process of like all the stuff that we needed, and at this point we're about to use weights, so I'm defining weights. But actually the weights are the same for the centroids and through each iteration, so that's really kind of dumb to be redefining the weights every single time. It's not a hugely costly process, but it costs, and there's no point to keep redoing it. So anyway, weights, it shouldn't be in the for loop, and it really shouldn't even be in the while true loop. It should be defined like right above while true. So anyways, just thought I would throw that in there. I'm sure I've made lots of other stupid calculations. I've just happened to catch this one, so I'm bringing that up. So we have our weights, and then for feature set in data, what we're going to do is, let's see, if np.linalg norm, we're going to pretty much redo this entire thing. So what we're going to do for feature set in data, so I've cleared out everything in that for loop. Now what we're going to say is distance equals np.linalg.norm, whatever that feature set is, feature set minus the centroid. So now we have the full distance. And then what we're going to say is if the distance equals 0, we're going to say distance equals 0.01. Okay, something like that. That might be a little too absurd. Maybe that. Okay, so basically as you could also say like, never mind. But anyway, this is just for when the feature set is comparing distance to itself for that first iteration. So we're just going to do this to make it simple. So now what we're going to say is the weight index equals the integer value, so it's just going to kind of like round it, of distance divided by self.radius. So what's that entire distance? And then we're going to divide that by that radius, that distance that we wanted to work with. So the entire distance divided by the radius, that's basically how many radius steps we took. And the more steps that we take, the less we want that weight to be. Right? So if the weight index is 0, the weight would be 99. If the weight index is 3, so if there are 3 radiuses in that distance, that's further away, we would want that weight index to be 3, and that would correspond to 96, right? Or, I don't know. Anyway, somewhere in the mid-90s. Anyway, weight index. Now, we're going to say if weights underscore index is greater than self.radius underscore norm underscore step minus 1, we're going to say the weight underscore index equals self.radius underscore norm underscore step minus 1. What's happening here? Okay, so if the distance is just greater than that maximum distance, so if it's more than 100 steps away, we're just going to say the weight index is that max element, which in this case would be, in theory, like 0. So so if it's outside of all of the bounds, we're just going to say that's the weight value. And then we're going to say to underscore add, and we're going to say that value is weight index to the or squared, or to the power of 2. So we're squaring that times the feature set, and there we have that. One thing I'll add is I'm not really sure how to implement it very well in this code, because without making it probably too tedious. But for example, one way that you can do like averages without actually doing what we're doing, because in theory we're multiplying the size of our data set. This is going to be a huge, in theory, a huge array, or list in this case. Right, it'll be a huge list of features, and then we're going to average that huge list, where one thing that you can do is you can say, okay, here's a number. There are 100 of these numbers, and then that makes just one big number. And then you could say that big number divided by there's 100 of these. That's easier to do than making an array that has 100 of those numbers and then calculating the mean of 100 of those numbers. That's going to take up more space in your memory. So something like that could be added to this, but again, this is just meant to be a really simple example to showcase weights, not to actually be super efficient. But anyway, keep that in mind. Basically, at this point, when we create this we're making a very large list in theory. It's 100 times each feature, possibly. So you're multiplying your data set quite a bit here, plausibly. So keep that in mind. So anyway, to add, and then what we're going to say is we're just going to say in underscore bandwidth plus equals to add. So you can, when you have like two lists, this is a list plus a list. Okay, so that's why you can do plus equals there. Okay, so now what we've got is we're going to come on down to new Centroids. Let me think here. Let me make sure. So np.average and bandwidth, that's fine. We get the new Centroids, the tuple, cool, uniques. That's fine. And so yeah, basically between uniques and prev Centroids, we need to add a bunch of code. So we're going to say two underscore pop. It's going to be empty list. And then we're going to say for I in uniques. So for each element in uniques. And then for I in, we'll do this. Let me think if this is legit. For I in uniques, and then for I in. So this is just kind of like a way that we're gonna. Sorry, I'm trying to think if I'll get away with this. I think you could do for I in uniques and then for I in uniques. That should work. If that doesn't work, we'll come through. I can't imagine a reason why that won't work. Anyway, if I equals I, we pass. Okay, so if they're identical, we pass because it's going to be equal to itself. But we've already, the ones that are totally equal to each other, we've already identified those when we did the sorted list set. So if I equals I, it's literally itself. Okay, so we're not worried about that. And the whole reason for this new code that we're doing is because we've made this size much bigger, we're in theory incorporating a lot of other data points. So there's going to be centroids that are like really close to each other, but not perfectly equal to each other. And we need to be able to get rid of those because those are useless, right? We don't need them. Like if they're, 0.001% different from each other, why would we have those? That doesn't make any sense. So we're going to get rid of those, and this will be a sort of tolerance-ish kind of thing. Anyway, if they are equal to each other, we pass because of what I just said. We've already got the set, so that would be purely itself. Elif np.linalg.norm of np array I, and then np, whoops, it's minus, np array I minus np dot array I. Let's see, if the distance between these two, if the distance between these two arrays, or vectors, or whatever you want to envision them like, if that distance is less than or equal to the self.radius, so if they are within one radius step of each other, we're going to say these need to be converged to be the same centroid. So if they are within that same one step of each other, and keep in mind, how many steps do we have? We have 100 steps in the data set, so that's a lot of steps. So if they're within just like that one original step, what we're going to do is pop it out. So we're going to say to underscore pop dot append I, and then we're actually going to break here. So I'll show you what happens if we don't break there later. But anyway, to pop append I. Now, once we have the two pops, and just real quick, why can't you just pop I right away? You can't modify the list as you iterate through it. Okay, so that's why we have to kind of do it this way. Now, we're going to say for I into underscore popper. In a lot of cases, you'll get an error. Sometimes you won't get an error. I think you'll get an error for sure in a dictionary. I don't know if in a list, but it's not a good idea to ever try to modify a list as you iterate through it. For I into pop, we're going to try to uniques.remove I. And in fact, we probably don't need to have a try there because that's why we added that break. But anyway, if we don't have the break there, we'll probably add like twice because there's going to be like one versus each other. So we'd probably add twice if we didn't break there. So anyway, we probably don't need that try and accept, but anyway, we'll show an example of that whenever we go through it. So now, let's see. Now what we're going to do is self.centroids equals centroids. So basically all the way up to this point, the code is done. We should everything should work. Let's go ahead and run it and just see what we get at this point, because I think that's all the major code changes we wanted. List uniques.remove I not in the list. Let me go ahead and add. I'm pretty sure for I and to pop append. Let's go ahead and just have the try and accept here real quick. I thought that break would save us, but anyway, accept, pass for now. Let's just see what happens. Okay, so it worked out in the end. I wonder why there would be two cases of the same pop. Anyway, I'd have to think about that later and really look at the code. But anyway, so we've got the clusters. It's not as perfect of a cluster as we would want, most likely because we popped. This one looks pretty good. This one looks eh, and this one's eh. But if we are to actually classify these clusters by the cluster center, then that would be a successful one. Also, this is a very small problem. So because of that very few number of data points, that could skew the centroids a little bit. So anyway, that's that. Now, let's work on adding classifications and then actually allowing this code to scale out a little bit to bigger data sets, and we'll show an example there. So now after, let's see, self.centroids equals centroids, great. We're going to say self.classifications, and that's going to equal an empty dictionary for now. And we're going to say for I in range of the len self.centroids. And we're going to say self.classifications I equals an empty list for now. So we're going to classify by, cluster 0, 1, 2. We've kind of done this. I'm pretty sure this is similar code from the k-means. And then what we're going to say is for feature set in data, we're going to say the distances equals, we'll make this a list of lists, np.linalg.norm of the feature set minus self.centroids, centroid, and then that would be for centroid in self.centroids. Good, it's not running off the screen. For centroid, okay, good. So those are our distances. And then we're going to say the classification is that minimum distance, right? So that would be classification equals distances.index, and then it's that min of the distances. So whichever centroid has the least distance, that's the classification. That'll be the classification index, basically. And then we're going to say self.classifications, classification, right? So that's the classification of that feature set. So we're going to say that classification now gets an append of that feature set, because now we know it's a part of that class. Okay? So once we have that, good. Also, we can take this here and paste that under predict. So distances, classification, self.classification. Or rather, actually, we just need distances and classification. And then we return classification. So now our predict class is completed. Now we should be all set. So then what we're going to do is we're going to pop on down to, we've got centroids, p.42 scatter, great. Now what we're going to do is, for C and centroids, we'll leave this code here, but then we're going to get rid of this code. And we are going to say for classification in clf.classifications, what do we want to do? Well, we're going to say the color is equal to colors classification. So we're just going to use that as an index. Let me make sure we multiplied that list of colors. Where's my bar? There it is. Yes, we did. Okay, coming down. Classification. Fix that. And now we're going to say for feature set in clf.classifications classification. Okay. plt.scatter. And then this will be feature set. Oops. Feature set 0, feature set 1, and then we're going to say the marker will be, we'll do X here, and then color will be just color, because we've already color, because we define color here. Color is equal to color, S equals 150, and that's probably all we really need. And then plt.show, we're done. Whoops. Great. Let's look at that real quick, make sure that worked. Ooh, we need to change the line width. here. Let's say line widths equals 5. Great. Okay, so we got the clusters. That worked out. Fab. So now what we're going to do is we are going to pop onto the top here, and we're going to make blobs from scikit-learn. So from scikit-learn.datasets.samples generator import make underscore blobs. Now what we're going to do is, let's comment this out before we forget. We are going to do, let's say x comma y. We're not going to use y, but it always, when you make blobs, it will classify the blobs for you, just for a favor. Because when you make blobs, you might be doing SVM, or you might actually be doing SVM and training a classifier, or you might be trying to do clustering. So it can do both. Anyway, get you a blob that can do both. Make blobs equal, or no, make blobs n samples. And we'll start with a 15. We'll say centers equals 3. And then we'll say n features equals 2. And then what we can do, actually, let's run this one first, and then we'll play with that in a second. So let's say XY. Everything looks good. Let's do it. Wait for it. Okay. So this one, it gave us only one centroid, even though clearly probably should have had one there, there, and there. Let's try again. Let's try again. And before they all mess up. Okay, so this one's a little different. This one probably wanted you to be there, but it did at least get this cluster and this cluster. Hopefully, I'm hoping it's going to give us like something like totally obvious, so we can be like, yeah, good job. Yeah, so this one's totally obvious, and we can say, yeah, good job to our clustering algorithm. It figured out, yep, that's correct, that's correct, that's correct. Awesome. Okay, so that looks good. Let's increase samples. Again, as usual, if you're on like a smaller computer or something, you might not want to do as many samples. And if you did, like, you could change the radius step smaller, because that's going to make a huge difference on your processing time. Wow, are you serious? I'm very angry at that one. I'm going back to the 100 steps, so we get the proper looking classifications. I don't think the 100 steps would have made that mistake. All it's taking forever to come up. While we wait for that, we're going to import random, and then for centers, let's say is going to be I cannot believe it's still not coming up. It must have come up and now it's under here. Let's see. It didn't get it. Oh my goodness, this is embarrassing. Here, we're gonna decrease these samples here. Let's do 50. Hopefully it'll be a little quicker. Yeah, the second one really should have come through. It's embarrassing. Wow, we might just have to keep number of samples to like 20, because this takes forever. Oh, it just popped up. Hold on. Oh, at least this one worked. I don't understand. That's pretty confusing how some of them work totally obviously. Even this one's like pretty close. Like, I wonder why some of those ones where they're close like this, usually it's like got a cluster center right there, and then you've got this one. I wonder what causes that. But anyway, that one worked. So what I want to do is we'll say centers equals random.randRange, and let's do between 2 and 8, and we'll just randomly centers, and then let's run it. Let's just see. Let's see what we think when we see it, and we'll see. Oh my goodness, this is messy as heck. Oh my lord. I wonder. Let's see. So looking at just the this is kind of hard to see. Let's see. You got one cluster here, probably one here. So 1, 2, 3. I don't. This is hard. 4, 5, 6. 6 total clusters, I think. That's what I think we have there. And then let's come over here. Print or centers. Oh, it was 7. I wonder what they were. Oh wait, let's see. Center. No, we can't get it now. But okay. Maybe we probably need more samples if we're gonna do 8. Let's go up. We'll be willing to go up to 5. Yeah, this one probably has 1, 2, 3. It might have 5 or 4, but unfortunately we clearly didn't get them all. Print centers. Actually, that one only had 4. I wonder what those ones were. But as you can see, there's some significant standard deviation going on. So you might want to tinker with the standard deviation. That's probably throwing us for a loop a little bit. But anyway, so I think that'll bring a wow. Yeah, like this is another case where you probably have too many, or too few samples rather. Anyway, but our code is pretty darn slow, so that for sure, even though we were maybe a little faster than scikit-learn with k-means, with mean shift, we are definitely the losers here. So anyway, that's all for now. This is a really simple, stupid example of mean shift, but as you can see, it's a big deal. Either hard coding the radius is just lame and stupid, or having to choose that value yourself. There are various ways that you can choose the radius and automatically find it. You can probably think of a better way to do it than ours. Again, I'll just say that most likely the largest hang-up in our code is this part here, where we're multiplying and we're creating, in theory, a huge vector that might take a while. But then again, I mean, that was taking a lot longer than I would have expected, even to have, let's say, 50 samples times 100. I mean, that's like 5,000 samples. So why is that taking a long time? I don't know. That shouldn't take that long. But anyway, this is just supposed to be a nice custom version that just gives you an idea of how it works, not necessarily so you can have something that's going to win you competitions. So anyway, that's that. If you have suggestions about how to improve this, if you can figure out a much faster way or a more reliable way, I'm all ears. There are various things you can do, like you can modify the weights, you can modify the step, and you can modify here, especially we're squaring the weight. So, so it's not 100 times 50. We are squaring that value. So that's probably, let's just for kicks, it's going to make a big difference in accuracy. But let's 50 sample. Let's do, yeah, we'll keep 50 samples. Let's see how quickly that comes up. Yeah, so that's like really fast. And then even though it did affect our accuracy, so it's much quicker if you don't square it, which makes sense because you know, let's say the weight is 30 squared is a big number. So so that's what's doing it. But again, if there was a decent way to add them to the list and say these were worse, so like maybe you could make a weight dictionary and then add everything to the weight dictionary that had those weights, and then when you went to go do the average, you would just have one big number and you would say, okay, this big number constitutes X data points, X number of data features or whatever. That would be a much easier process on the machine to do. So anyway, this is clearly the area for improvement. If I just multiply by 2. Oh, we got an empty sequence there. That's not good enough anyway. That's no surprise. That's a pretty surprising. Anyway, now I'm just embarrassing myself. If this is not the best code you've ever seen, I don't know what is. But anyway, that's good. We'll end on this note. Anyway, questions, comments, additions, changes. I'm excited to see if anybody can come up with something better. I'm sure somebody can. So feel free to share if you come up with something good. Anyway, now we're going to be moving on to a recently much more popular topic, which is the neural network, which has kind of evolved into deep learning and all that. So we're going to be changing gears now, talking about neural networks, which are actually extremely simple at their base form, but then they get very complex very fast. So anyways, we're going to be transitioning into the neural network. Questions, comments, concerns, whatever, leave them below. Otherwise, till next time.